Hello, welcome to today's talk on Coulomb's law. What are we learning? What is the relationship between force, charge, and distance? And we're going to compare and contrast the electric force to the gravitational force. In these two figures, we see two charged particles, and this one two positive charged particles, and the one next to it a positive and a negative. Notice that the electric force can be repulsive when the charges are the same, and they are attractive when the charges are opposite. The relationship between the force here and the two charges and the distance is given in Coulomb's law, where the force will equal Coulomb's constant, which is 8.975 times 10 to the ninth newtons meters squared over Coulomb squared. And we're going to take that, multiply it by the charge in coulombs of the first charge, times the charge in coulombs of the second one. Notice that we're using the absolute values here. We are finding the magnitude. Now we're going to take all of that and divide it by the distance squared. This is an inverse square law. If we take a look at the basic function y equals 1 over x squared, this is the shape of the graph that we'll find for Coulomb's law. And it was the same with the gravitational force. If we look through this graph here, obviously this is 1 over 1 squared. At 2, it's 1 over 2 squared, or 4. At 3, it's 1 over 3 squared, or 1 over 9. And at 4, it's 1 over 16. Let's compare and contrast Coulomb's law and Newton's law of universal gravitation. Notice that they do look the same. You have a constant here. Here it is the Coulomb's constant, and here's the gravitational constant, and here's where the first big difference is. Coulomb's constant is very large, a number times 10 to the 9. The gravitational constant is very small, some number times 10 to the negative 11th. Also, electric forces can be attractive or repulsive. Gravitational forces are only attractive. In Coulomb's law, we have the product of two charges. In Newton's law of universal gravitation, we have the product of two masses. But both are inverse square laws. They are both divided by the distance squared. Let's try a calculation here. Let's say we have two charges, and those charges equal our constant E. So they could be a proton and an electron. And how much force do they have on each other over a relatively large distance of 2 meters? They'll be an attractive charge because they are opposite charges. Here's our Coulomb's law equation. Coulomb's constant times the product of the two charges divided by the distance squared. Let's plug and chug. Notice that we're using scientific notation all around. These are very large and very small numbers here. And we see that the force is 5 times 7, 5 times 10 to the negative 29 newtons. Very, very small. Let's summarize what we know. First, Coulomb's law tells us what the force is between two charges in relationship to their distance. Force is directly proportional to the product of the charges. Force is inversely proportional to the square of the distance between those two charges. These forces can be repulsive or attractive, and it is much, much stronger than the gravitational force. And where we see that is here in Coulomb's constant here, which is a very, very large number, whereas the gravitational constant was a very small number. All right, complete your Cornell notes, rewind, and review as necessary. Thanks for listening.